stress design and load and resistance factor design using the 2005 NDS. And today we're going to focus specifically on connection design. Our outline for today is fairly simple. We're going to talk briefly at the beginning about connection philosophy, and that's more or less dealing with issues from a broad perspective related to connection design. And then we'll get into a chapter-by-chapter discussion for the connection provisions of the NDS. Along the way, we'll talk about changes from previous editions of the NDS and throw in some example problems along the way. As I mentioned, this is part 2 of a 2-part series. Part 1 was conducted last month and is available on the Woodworks website. The link is shown there on your slide. So if you missed that and want to go back and review, you can get to that on the Woodworks website, and it's a streaming recorded version of our first session. So without further ado, we'll jump into this and talk a little bit about connection philosophy. The biggest thing I hope you take away from today's session, if nothing else, is that tension perpendicular to grain is the weak link for wood products. And we state several times in the NDS that you need to avoid loading wood members that would create that type of stress in a wood member, and reinforce if you're not able to avoid those conditions. So we'll talk along the way today about several do's and don'ts for avoiding tension perpendicular to grain. Some initiators of that include notching or hanging loads off the tension side of a bending member, or eccentricities that can be incorporated into a wood member with web members, for example, in a truss coming in at different angles and not centered on a point like at a pin type connection. Here's a real simple first approach at dealing with that issue, and that's with notching of wood members. And this relates to connections because we'll obviously see different types of connections at bearing locations. We'll show a couple of examples of that before we actually jump into the chapter-by-chapter description. But obviously, if you notch a wood member, as shown there on the left, that can lead to splitting of the member, if not with the initial load over time. And so the solution is to try and avoid notching whenever possible and just go with direct bearing on the wood member. Another example of a connection that can cause tension perpendicular to grain stresses is hanging a load off the bottom of a beam in the tension zone. And again, this is not recommended because it can lead to splitting because of that tension perp stress in the wood member. A better solution would be to try and get that connection up in the compression side of the bending member, or better yet, create a saddle type hanger over the top of the member to carry the load and not even worry about connections through the member itself. Here's another example of that notched beam bearing condition that we talked about earlier, where you can potentially end up with splitting. And a better solution then would, if you have clearance issues where you can't go too high with a wood member in a structure, perhaps then you could notch the bearing wall to take care of those issues. So again, we're avoiding notching of the wood members at all costs. Here's one that may not seem as obvious, but that we see in the field and can lead to problems, and that's if you have a sloped beam that's not fully supported along the entire length of that slope. as you can see here, you could cause splitting because you're exposing the end grain, and you're still going to have high shear forces there at the end of that member, and so you could have a problem with this type of connection as well. A better solution, again, is to get full bearing of that entire sloped area at the bearing location, and ensure that you're not creating any additional stress perpendicular to grain in the wood member. And if I'm going pretty fast, the reason is because in our first session, if any of you joined us, we started to run out of time near the end. So I'm going to clip right along as quickly as I can. We've got a lot of material to cover, and then hopefully leave as much time as possible at the end for questions. So we'll jump into the chapter by chapter discussion of the NDS. Again, in the first session, we dealt with the first 9 chapters and then the last 3. In this session today, we're going to focus specifically on chapters 10 through 13, dealing with connections, and Appendix E, which deals with local stresses in fastener groups. And that's a very important part of connection design that we want to cover here today. So, Chapter 10 gives more or less the broad overview of connection design, gives the table with all the adjustment factors and how they are applied to different types of connectors. Chapter 11 then deals specifically with dowel type connectors, bolts, nails, lag screws, wood screws. Chapter 12 deals with split rings and shear plates, and then Chapter 13 with timber rivets. So we'll jump into Chapter 10 first and talk more about some of the adjustment factors, and first we'll talk about this issue of local stresses in connections. When we have multiple fasteners, 10.2.2 of the NDS says that local stresses in connections using multiple fasteners shall be checked in accordance with principles of engineering mechanics, and then a reference to another section of the NDS, which is this section. And here we give a link to Appendix E, which is one method for determining the stresses in those multiple fastener connections. So let's take a look specifically at Appendix E. Again, you know, we talked a little bit about philosophy of connection design at the beginning. This kind of further continues that discussion of philosophy of connection design when we're talking about local stresses in fastener groups. And as we move through the examples here, I think you'll understand a little bit better what I mean by that. What we found when we did research at the USDA Forest Products Lab up in Madison, Wisconsin, on some large bolted connections, is that closely spaced fasteners can lead to brittle failures at lower capacities than you would get just calculating the connection capacities by themselves. And so a wood failure mechanism needs to be considered in the design process. And that's always been stated in the NDS, but it was never, there was never any type of solution provided. So that's what was developed in 2001 to try and deal with this issue. The bottom line from the research is that the better connection is one in which the fasteners are spread out to the extent possible based on other limits in the NDS. This gives you increased ductility and higher capacity in the wood member. Again, there are two different things that we're dealing with here, and we'll talk specifically about connection design values in a little while in the seminar, but for now we're talking about the wood capacity around those fasteners or around that group of fasteners, and that's what Appendix E tries to address. So if you look specifically at the equations, there are three sets of equations in Appendix E that deal with this issue. The first being net section tension of the wood member. And as you see in the first drawing here at the top, and let's see if I can find that little highlighter tool. In this area here, we've got tension through the wood member, and so that net tension check is what we're looking at with this equation, which is simply the tension value times the area. The second one then deals with row tear out, and that is calculated using a horizontal shear value then times the area encompassed by these fasteners along this row. The third set of equations deals then with group tear out, and it becomes more or less an interaction of the two, where you have net tension, like we calculated with the first equation, and horizontal shear along the outer extremities of this fastener group. And a note here at the bottom is something that we'll come back to a couple of different times, because connection design is sort of a trial and error process, if you will, where there are several different considerations in the process along the way that you need to account for. We're dealing with this issue of local stresses in fastener groups, but one of the other requirements in connection design is that the spacing between outer rows of fasteners cannot exceed 5 inches. And that's because of the tension perpendicular to grain issue that we talked about earlier in the discussion. And so let's move on with discussion of Appendix E, and I think you'll see how all of this comes together in the example problem here in just a second. And again, to reiterate this whole issue of spacing between outer rows of bolts, Table 11.5.1D of the NDS specifically shows that requirement for a maximum of 5 inches between outside fastener rows. And so wanted to make sure we see that up front before we go too much further into the example problems. So let's look at an example of a truss bottom cord with a splice. We'll have a total load, dead plus live, of 20,000 pounds. And we'll assume a dry moisture service condition, unincised material, low duration factor of 1. So we're not going to have a lot of additional adjustment factors come into play for this particular example problem. So we're going to do the connection design, offline. That's already been taken care of, and we determined that we need 2 rows of 7/8 inch bolts as shown here in this pattern. For the NDS fabrication requirements, it's going to require 1/16 inch oversized holes, and so we're going to check the local stresses to verify the member size here. First thing we'll do beyond the connection design itself is make sure that we've got a tension member that's big enough to handle that 20,000 pound load. And so we'll go to a selection table in one of the manuals that's part of the NDS package, part of the wood design package. We'll try a 4x12 #1 hem fir and see that that has a capacity of 24,600 pounds, so more than enough to carry that 20 kip load. And again, since connection design oftentimes is a trial and error approach, we'll first try just spacing all these rows evenly along the depth of this member at 3 3/4 inches. We'll use a single shear steel splice plate. It's probably not the best approach. You probably want to use double shear so we don't have to deal with eccentricity, but for this particular example, we'll just ignore that eccentricity created by a single steel plate on one side and go with that spacing. So first, again, we're going to tackle the net section tension that we talked about. And so we're going to start with the depth of the member at 11 1/4 inches, and we're going to deduct the 7/8 inch bolt and the 1/16 inch bolt hole from that cross section to come up with a net section of 32.8 square inches. Then we're going to multiply that times the tension value of that 4x12 hem fur, and you see that we come up with a capacity of 20,500 pounds, just a little more than what we need, but obviously less than the full capacity of the wood member. Then we're going to check the row tear out capacity. And so from the NDS supplement, we're going to use a shear value of 150 psi. We're going to use the critical spacing, which is the lesser of the end distance or the fastener spacing. So we're going to use 4D for that value. And using the equation from Appendix E, we come up with a capacity 29,400 pounds, well in excess of the 20 kip load that we need to cover. So then the third equation is this group tear out equation. And so we're going to deduct or calculate that net group area there as part of the equation. And again, we're moving quickly, but you can go back and check these numbers on your own since you have the handouts. We come up with a capacity of 20,850 pounds. Again, more than what we need for the 20 kip load. So the design is still acceptable. Net section tension, if you recall, was 20,500 pounds. That's what controls of these three checks that we made. But let's experiment with this a little bit and see how spacing the fasteners can impact the design. So first, let's put that maximum spacing of 5 inches between rows. As you'll recall, for a steel plate, that's the maximum that we'll want to space these bolts. And again, it comes back to that tension perp issue. If you've got a steel plate and steel bolts, which aren't affected by moisture content, but you've got a wood member which may shrink as it goes into service, then you can imagine that if these steel bolts here stay in place because of the steel plate, it's going to tend to want to split the wood member along the length here. And so that's what that 5-inch max is doing, is helping to deal with that tension perp issue. But when we move that out, what we've done is we've basically increased the area here along this cross section. And so, in effect, we've increased the capacity by about 7,000 pounds. So you can see it's a pretty significant increase just based on increasing the spacing between fasteners by, what, 1 1/4 inches. Now, let's go the other direction. Let's say we decrease the spacing between those rows to the absolute minimum, which is 1.5 diameters. And in that case, 1.31 inches, a very tight spacing. But what we've done, in effect, is reduced this cross-section here and reduced our capacity to well below the 20,000 pounds that we need. So you can see the impact that spacing of rows has on the design process. So it goes back to an earlier statement that we made about spreading out the fasteners and getting those to a point that is not going to lead to any type of wood failure with these large bolted connections. So we'll move on from there and talk a little bit more about some of the other adjustment factors that apply to connections. This table in Chapter 10, Table 10.3.1, lists all of the various adjustment factors that apply to different types of connections. We'll look at just a couple of those. Again, in the interest of time, we'll keep moving along. We won't have time to deal with every one of these adjustment factors, but we'll look at a couple of them and run some more examples to give you a good feel for how they apply in the NDS. So first, let's tackle the group action factor, C sub G. This factor also applies to multiple fastener connections, but it is different from the Appendix E criteria that we just discussed a few minutes ago. This C sub G factor actually accounts for the load distribution within the group of fasteners. If you have a series of fasteners all grouped together, we've seen from testing and just based on fabrication tolerances that certain bolts or certain fasteners in that connection group will start to pick up load before other parts or other fasteners in that group. And so this group action factor accounts for that load distribution, if you will, or redistribution, if you want to call it that, inside of that fastener group. And it applies to split rings, shear plates, dowels. There are tabulated values for the group action factor in the NDS, and there is an equation that can be used if you fall outside of that tabulated range. Before we go there, you need to be aware of the various definitions that exist for what we consider a row of fasteners in the NDS. And this becomes particularly critical when we're talking about staggered rows of fasteners. And so these graphics in Chapter 10 help to define what is considered a row of fasteners as it relates specifically to the group action factor calculations. So I mentioned that the tabulated values are there, but if you like complicated equations, which I believe this is one of the most complicated that we have in the NDS, or you don't want to extrapolate beyond the tabulated values, this equation exists and allows you to calculate the group action factor per the NDS. And we'll work through a quick example here and look at tabulated values as well. But basically, the equation incorporates a load slip modulus for various types of fasteners. For bolts and lag screws in a wood to metal connection, you see there is one load slip equation. For bolts and lag screws in a wood to wood connection, there's a different load slip curve that's represented by this equation. And then for split rings and shear plates, values as well for that load slip term. So let's look at an example. Let's say we have two rows of 1-inch diameter bolts spaced 4 inches apart, wood to wood double shear splice connection with 2x12s. You see that the stiffness of the main and the side member is 1.4 million psi, and then we show the various main and side member cross-sectional areas, which are also used in the equation. Again, I won't bore you going through each and every one of these steps, but you can look at that on your own. You calculate the various parts of the equation, come up with a result of 0.669 for a group action factor. That would then be applied to the Z values, the cumulative Z values that you calculate from the individual bolt equations. Now, let's look at the tabulated values. Again, unless you're a glutton for punishment, the tabulated values are here and show the values based on cross-sectional area of the main and side members and some ratios that you can develop from that. In this particular example, we end up with a ratio in the first column of 0.5. We've got 10 fasteners in that row. The A sub M value, according to note 1, is the same as the one that we would use for A sub S, and it's 16.875. Well, obviously we're going to have to interpolate in this table. We only have values shown for 12 and 20. So you work your way across, end up with two values there that you interpolate. You end up with a 0.665, which is 4 1,000ths from where we calculated with the equation. So close enough for this exercise. The other question that often comes up has to do with the application of this group action factor to situations like this. In the example we looked at earlier, it was a bottom chord of a truss where you've got a group of fasteners with an axial load in that tension cord of the truss. And so seeing how load gets applied to those fasteners with that axial load and that tension member is pretty straightforward. However, when we look at a bottom plate of a shear wall, for example, with anchor bolts and washers spaced per, in some cases 2 feet on center, 16 inches on center for large capacity shear walls, the question comes up whether the group action factor applies here. And our interpretation that we give, and it's in an FAQ on our website, is that it's not applicable here because the loads acting on this shear wall are really not the same type of loads that you'd see in, for example, the truss bottom chord that we looked at. You're picking up unit loads along the length of the shear wall, along the bottom plate. And so we don't consider that to be the same. We think the fasteners, the anchor bolts, if you will be picking up load in a pretty uniform fashion along the length of that bottom plate, and so it would not apply in this particular situation. Okay, we'll move on to wet service factor, C sub M. And unlike wood members, that C sub M factor also applies to wood members, and you adjust your strength and stiffness values for a wood member. But that applicability to wood members really is based on what the wood member will see in service. For fastener design, we're not only worried about what the fastener will see in service, but we're also worried about what it will see at time of fabrication. And the reason for that is because at the time of fabrication, let's say if a wood member is fabricated in a wet member, something at or above 19% moisture content, as that wood member dries down, stress fractures will occur around the fasteners, whether they're bolts or nails, and that will affect the capacity of the fastener. We've seen that through testing. And so that's why when you look at the table for wet service factors for connections, you're going to see a column for the fabricated moisture content and the in-service moisture content. And for large diameter fasteners, greater than 1/4 of an inch, it's a pretty substantial reduction, 0.4, if you are fabricated wet and then that fastener dries down in service. Now there are some exceptions to that. For the smaller diameter fasteners, less than 1/4 inch, that reduction factor is not as significant. It's only a 30% reduction versus a 60% reduction. And then there are a few other exceptions as well. I'll show on the next slide. If we're just talking about one fastener or a row of fasteners, or if we properly fabricate the fastener so that you keep, again, deal with that tension perpendicular to grain issue, then you're not going to see as dramatic a reduction due to that wet service factor. So there are a lot of different checks along the way in the design process to make sure that that tension perpendicular to grain stress that we've talked about so much in this design process does not affect the capacity of your connection. And again, we come back to the slide showing that we need to space those fasteners at least 5 inches apart if we've got steel side plates on wood main members. As we mentioned early on in the program, the 2005 NDS does apply to both allowable stress design and load and resistance factor design. So the table, as we talked about in the first session a month ago, is set up to give you a pretty straightforward approach to allowable stress design, where you would start on this side of the table and work your way across with these adjustment factors, versus LRFD, where you would exclude that first column, which is applicable only to allowable stress design, the load duration factor, and start here with your wet service adjustment factor and work your way across. Again, if you need to get up to speed on that whole LRFD process, we covered that pretty extensively in the first program. I'd encourage you to go back and take a look at that at your convenience. So what types of fasteners are covered in the NDS? Well, we've touched on some of them briefly already. Bolts, lag screws, wood screws, nails, and spikes are covered by the NDS, but are also covered by national evaluation reports for many of the proprietary products that are out there. Now, to our knowledge, split rings, shear plates, and drift bolts and drift pins are only covered in the NDS. And then there are products like metal connector plates that go on trusses, hangers and framing anchors, and staples and pneumatic nails that are only covered through evaluation reports. One of the questions we get a lot is about capacities for staples or pneumatic nails. And the NER that covers those products, if you want to jot this down, is through the International Staple and Nail Tool Association, abbreviated ISANTA, I-S-A-N-T-A. And if you do a Google search, isanta.org is the first website that pops up, and you can get copies of that evaluation report for pneumatic nails and staples directly from the ISANTA website. So we're going to start into a discussion of connection design for the yield equations in the NDS. And to do that, we want to give a little background on the capacities, the material properties that are required to use those yield limit equations. The first of those is the fastener bending yield strength, and that's more or less the moment capacity of the fastener. And we tabulate those in Appendix I, as in India, at the back of the NDS. This is Table I-1, which tabulates those bending yield strengths for bolts and lag screws at 45,000 psi, and then the nails or hardened steel nails. Those values are for the most part determined from center point bending tests. For the larger diameter fasteners, it's actually a ratio of tensile yield and tensile ultimate strength of the material. But for the nails and wood screws, it's based on a center point bending test per ASTM standards. The other property that we need for the yield equations is our dowel bearing strength. And we tabulate those for both lumber or wood products, lumber and engineered wood products, or plywood. For lumber and engineered wood products, there is an effect based on fastener diameter. For fasteners with diameters less than 1/4 inch, there's just one dowel bearing strength. For fasteners greater than 1/4 inch, there is a variation parallel to grain versus perpendicular to grain. And so the parallel to grain values are tabulated here in this first column, and then perpendicular to grain values vary based on the diameter of the fastener. Start here at 1/4 inch, and then I truncated the table here, but work their way across and are tabulated based on diameter. The equations are also shown in the footnotes of the table. So if you have spreadsheets that you've developed and want to incorporate those equations, then those are available as well. So then we get to table 11.3.1a, which lists the 6 different yield mode equations for single shear. There are 4 yield equations for double shear, not shown here, but are in that same table. And these would be used to develop wood to wood, wood to steel, and wood to concrete capacities for connections. Each of the 6 yield mode equations is calculated, and then the lesser of these 6 values is what controls for that particular configuration, and is what is tabulated in the NDS. And so if you were to look at a tabulated value, which we will in a little bit, it has already taken into account all 6 of these yield mode equations, and the controlling equation is what is tabulated. So what do those 6 equations represent? Well, the first 2 equations, 1M and 1S, represent really the capacity of the wood member. What we assume with yields 1M and 1S is that this dowel is sufficiently stiff that it's not going to yield. There's no hinge forming in this particular dowel. The 1M, the M and the S in the subscript represent the main member and the side member. And so 1M represents yielding of the wood fibers in the main member. 1S represents yielding of the wood fibers in the side member. Now, if your main and side member are identical, same specific gravity, then you could get a case where the fastener is stiff enough that it rotates through in this fashion, and so you've got yielding in both the main and the side member. That's what we call a mode 2. Mode 3 is where we start to see an interaction where there is yielding of the fastener. So you see a hinge forming on one side of the shear plane in this particular fastener, but you still have yielding of the wood member, of the wood main member, so this would be a 3M control. Side member yielding here would represent a mode 3S control. And then mode 4 is where we are almost purely controlled by bending yield of the fastener. And by the way, this is our most ductile type of connection. So what the equations allow you to do beyond just the tabulated values is the equations would allow you to design ductility into your fastener or into your connection for loads that would require additional ductility. If you have wind or seismic loads where you want ductility built in and reducing the chance of a brittle failure, you could design your connection for a mode 3 or a mode 4 yield to get that ductility into the connection. The reduction terms are shown in another table, 11.3.1b, and they are different for the different yield modes and for different fasteners. The reason for that goes back to really the legacy versions of the NDS. 1986 and earlier editions of the NDS were all empirically based for connection design. There were no equations, and so the values were tabulated empirically based on tests. When we developed the yield mode equations, we tried to harmonize those with those earlier versions of the NDS. And so we ended up with different reduction terms. To give you an idea of what's coming in the future for the NDS, we will at some point be moving to an ultimate basis for connection design. And you'll see these reduction terms smoothed out into one single safety factor as we move to that ultimate basis. But for now, it provides us a way of maintaining consistency with those historical values. Oh, by the way, another question that often comes up is, are these the safety factors for fastener design? And they're only partial safety factors. If you look at the NDS commentary for the different types of fasteners, you'll see that we talk specifically about safety factors in the NDS commentary for different types of connections. So these terms are called reduction terms on purpose because they are not true safety factors. The safety factors are actually much larger than what's shown here for connection design. So then we talk a little bit about different types of fasteners. Nails, for example, we have box nails, common nails, sinkers, ring shank, and pneumatic nails. Those are all defined by certain different ASTM standards, but again, Appendix I, as in India of the NDS, shows the various diameters and lengths of those fasteners. Oh, I'm sorry, no, that's Appendix L. My mistake. Appendix I lists the bending yield properties. Appendix L lists the dimensional properties for these various products. So there's a table for the nails. I mentioned earlier that instead of using the equations, the values for different types of fasteners are all tabulated. And here we see a table developed for common box and sinker nails. But again, since the values are developed based on nail diameter, we can develop, for example, one value for, say, a 16-penny box nail, which has the same diameter as a 12-penny sinker nail. Here is a change that would be worth touching on, and that's the penetration depth factor. In the 1997 and earlier editions of the NDS, 91 and 97 I guess it would be, when we first developed the yield mode equations, the penetration depth factor was a separate factor from the yield limit equations. And that really had to do with the way we formatted the NDS at that time. As you may recall, We had a different chapter for nails, a different chapter for bolts, a different chapter for lag screws. And so since we formatted the equations in a different way, we had a penetration depth factor that was applied to nail or screw type connections. In the 2001 edition of the NDS, we brought all the yield limit equations into one chapter, Chapter 11, and we built that penetration effect into the yield limit equations. So if you use the yield limit equations in a spreadsheet or on our online calculator that I'll show you in a little bit, if you use the yield limit equations to calculate your connection capacities, that penetration effect is already built into those equations. However, if you strictly rely on the tabulated values, then there may be cases where you don't have the full penetration that we show in the footnotes to the table and are shown here for lag screws, wood screws, and nails. And if you have a reduced penetration, an easy way to come up with a value rather than having to run through all 6 of those yield mode equations is to use that adjustment P over 10D, which, as you'll recall, is the same format that we used to use for that penetration depth factor, C sub D. But again, to reiterate, if you are calculating values based on the equations, you don't have to, in addition to calculating those values, then take an additional penetration depth adjustment. There's a pretty extensive FAQ on our website that goes into a little more background on this, which you may want to take a look at some point. Now, we showed some penetration depth factors in the tables, and those factors were the penetrations that are required to get the full design value. The absolute minimum penetrations are shown here in this table, and these are the absolute minimums to get an adjusted value, or to get any value at all. And so if you fall below these minimums of 4D and 6D, your capacity for your fastener is 0. And we can show those graphically here in the next couple of slides. For nails, it's a 6 diameter penetration, and does, in the case of nails, include the tapered tip. For wood screws, also would be 6 diameters and include that tapered tip. For lag screws, however, we exclude the tapered tip, as shown here, and that value is shown in Appendix L. That value of E is shown. And so in your design process, you would want to exclude that tapered tip in the penetration calculations when calculating values. Another change to the 2001 NDS that created quite a few questions, and that we've developed some additional information for is reduced body diameter fasteners. And this primarily came about because we began to see lag screws in the field with reduced body diameters. And in earlier versions of the NDS, 1991, 1997, we assumed shank diameter for lag screws, and so the capacities were much higher. But since there was really no way of knowing whether the actual fastener would end up being a reduced body fastener versus a full body fastener, we went the conservative route and tabulated lag screw values based on that root diameter, D sub R. And that also forced us to look at even full body diameter fasteners where the shear plane could be in proximity to that root diameter, D sub R. And what happens if the shear plane is close to that root diameter, obviously the capacity can be lower because the hinge point that we talked about in some of the earlier slides could occur here in the reduced section of the fastener, even if the shear plane were here. And that's because obviously you have a smaller cross section here, and as you put a moment on this fastener, the reduced diameter is where it could yield. And so you'll see different, couple of different sections in the NDS. 11.3.6.2 is one of those that deals with that issue of root diameter versus shank diameter and how those are applied. And again, the maximum moment can occur in the threads rather than at the shank, and so that's why we had to go that route. We've developed a couple of documents. If you want to jot these down, or actually if you have the slides there in front of you, you might want to make a note. These are both available on the website, the AWC website, awc.org, to download. If you want Technical Report 12, which gives the mechanics-based approach for the yield limit equations, and then this design aid, number 1, which deals with application of that technical report for lag screw connections. And it gets into more detail with this issue of where that shear plane is relative to the threads, and allows you to take advantage of a higher design capacity if you know that that shear plane is going to be far enough away from the threads. For example, if you've got a steel side plate that you're connecting, and you know that that shear plane then will be far enough away from the threads, then you can take advantage of that larger shank diameter in the design process, rather than take the penalty that's in the tabulated values. So those are 2 additional resources that are available on our website. And again, that's applicable to wood screws as well. And these next 2 slides just show where the wood screw rolled threads versus cut threads vary, and how that root diameter then is used in the calculation process. One other adjustment factor that is pretty critical in the design process, if any toenail connections are used, there's a 1/3 reduction for toenails that are in withdrawal, and a 1/6 reduction in capacity for toenails in the lateral direction. Another question that comes up sometimes for new users to the NDS for the bolt and lag screw tables are these terms, these variables that are used to define different types of capacities in different types of joints. The Z parallel is pretty obvious, and in the first figure here, that just represents when all members are loaded parallel to grain. Z perp in that same vein is pretty obvious, as shown here in this figure, where both the main and the side members are loaded perpendicular to grain. And you might get something like this with say a single shear ledger connected to a glulam beam. The confusing part seems to come when we talk about ZM perp and ZS perp. And again, that goes back to how the wood members are loaded. ZM perp is represented in this diagram, where the main member, which is the center member here, looks like a 6x6, for example, is loaded perpendicular to grain by the side members, which are loaded parallel to grain. So the designation ZM-perp shows this particular configuration, again, where the main member is loaded perpendicular to grain. And then the opposite, ZS-perp, is where you have your side members, which are loaded perpendicular to grain, as shown here in this configuration. The main member is loaded parallel to grain. So you'll find these terms at the top of the tables for bolts and lag screws, and hopefully that'll clear that up for you. Two of these drawings actually show up in the NDS now. We're hoping to get the other two incorporated at some point to make it crystal clear. In the interim, again, these types of drawings are shown in an FAQ on our website. Another diagram that's shown in the NDS deals with spacing, end, and edge distance, and we don't have time to tackle that here in this seminar, but when we're looking at spacing between rows, spacing between rows of bolts, and spacing between bolts in a row, edge distances, end distances, these diagrams help define that. And again, as you look at those adjustment factors in the NDS, the values that are tabulated, the end distances that are shown, allow you to take a reduction if you are within a certain end or edge distance. And again, that goes back to making sure that you've got enough wood from the end of the member to the edge of the member to maintain the capacities that you tabulate for those types of fasteners. So let's take a look at a quick example of a cord tie between two shear walls, something like what might be shown here. We'll do an ASD LRFD side-by-side comparison so you can see how both of those work. So we've got a 16 gauge, 2.5 inch ASTM A653 metal strap across two floors, and we need to handle the hold down capacity of the shear wall up here on that second floor, transfer it down to the hold down on the first floor. So we're going to design a connection tie between those first and second floors. We'll assume a 2x6 Doug fir larch, and that uplift force at that location is 2,400 pounds. So one of the easiest ways is to go straight into the NDS table 11P, which tabulates values for an ASTM A653 16 gauge strap. We've got 10D common nails. So we're going to go into that table at the 16 gauge group near the top. We're going to come across for those, I think, to 10D fasteners, 10D commons, to the Doug fir column, and we see that the Z value for that particular configuration is 116 pounds. So let's look at the ASD side first, this column here. For a wind load calculation, the load duration factor that's used for all fasteners is 1.6. And I'll talk a little bit about that with respect to the yield modes in a second. But you can apply that load duration factor to those tabulated values. We've already accounted for the steel by backing out that 1.6 load duration factor in the Dow bearing strengths for the steel. So you would apply a 1.6 load duration factor. You're going to keep it simple. All the other factors are unity in this particular example. We take a look at the LRFD design. As we talked about in the first session, the time effect factor for LRFD has a baseline for lateral loads, and so the time effect factor in this case is 1. And then we have additional format conversion factor of 2.16 over phi and a resistance factor of 0.65. So we go to the next slide. We're going to calculate our loads. For the ASD, it's 2,400 pounds. For LRFD, it's 1.6 times that for 3,840 pounds. So again, tackling ASD first, we're going to have a z-value of 116 times that 1.6 factor times all the others, which are unity, bringing us to 186 pounds, requiring 13 nails. For LRFD, we take that 116 times our phi, a lambda of 0.1, that K sub F factor, and then all the other factors of unity, 250 pounds. In this particular case, LRFD does not give you an advantage over ASD. And there is a reason for that. I'll just show the final slide here to show that we have enough nails, 16 nails versus 13 nails to handle the capacity. The reason really has to do with the way ASCE7 has evolved over the years. In this particular case, since we're looking at wind load only, there have been some changes to ASCE7, and I think these are now straightened out in the 2010 version of ASCE7, and so we'll see that harmonized in the 2011 NDS. But you get the real benefits of LRFD are when you have multiple transient live loads, as we discussed in that first section. So if you're looking at wind load alone, there is actually a penalty in this version of the NDS. I think that is rectified in the next version of ASCE7 in the NDS. One last thing I want to show you with respect to the yield limit equations has to do with the connection calculator that's on our website. And it's pretty easy to find if you go to the codes and standards portion of the website and look for the calculators. There's a series of them there. And what the connection calculator allows you to do is actually put in a lot of the variables that we talked about. And again, this works for wood to wood, wood to steel, wood to concrete, all the species and grades of lumber in the NDS, even some connector diameters that aren't shown in the NDS are actually shown here in this connection calculator. And it actually shows all 6 yield modes here. And then obviously which one controls. As a result here in this particular example, mode 2 is what controls the exam. So hopefully you can take advantage of that. If you already have your spreadsheets set up, you know, that's fine. This might be a good way to actually troubleshoot and make sure your spreadsheets are working properly, but this is a free tool that's available on the AWC website. Okay, we're coming down the home stretch here. Looks like we're going to finish with plenty of time for questions. Chapter 12 covers split rings and shear plates, and there's really no change almost from the beginning of the NDS when these were first incorporated for split rings and shear plates. As I mentioned, this is probably one of the only places that the design process exists for split rings and shear plates in the U.S. And the question that we often get asked is, well, where do I even get those products? And the only company that we're aware of at this point that still sells those products is Cleveland Steel. And there's a website where you could go if you're interested in those products. The other chapter, connections chapter in the NDS, chapter 13 for timber rivets. is also unchanged from earlier editions of the NDS. I think timber rivets were incorporated in the 1997 edition of the NDS. And as you can see here, are used for various types of connections, from heavy timber trusses to beam to column connections. The rivets are a real high strength steel, AISI 1035 steel with a ultimate strength, ultimate tensile capacity of 145 KSI. The plates are ASTM A36 plates, and the tolerances for those, as you can see here, are such that when the nails are driven into the holes of the steel plates, they're actually, the top is actually mashed down to form a rivet type connection. It's a real tight connection that creates a real a cantilever effect for the fastener itself. And in the NDS itself, you're going to be looking at 4 different strength limit states. There's rivet yielding, both parallel and perpendicular to grain. There is then the wood failure mechanism, or limit state, both parallel and perpendicular to grain. And if you look at the wood failure mechanisms, you'll see that the same principles that we apply with Appendix E, which we started discussing at the beginning of the seminar today, where we're talking about local stresses in the wood members. These wood failure modes, parallel and perpendicular to grain, account for that same effect of capacity or local stresses in the wood member around those connections. So that's already built in to Chapter 13. You wouldn't do an additional Appendix E check of timber rivets if you use those for the design process. And just if you are interested, I mentioned that you know, with the hour and a half that we have here for these webinars, we're not able to go into quite the depth that we are with other programs. This actually is a derivative of a program that's on our website. It's part of our e-course section at awc.org. It's DES 110, Connection Design. It's actually on the website. It's a 3-hour course and provides up to 3 CEUs. And so those are available if you want to get a more comprehensive look and you're needing some CEUs. You can sit back and take a look at the audio-video portion that we developed in Flash to convey this particular seminar. So with that, I think we've actually finished a little early this time. I guess I overcorrected from our first session and shortened this one up more so than I did in the first one, but that does leave us plenty of time for questions. So I'm going to take a look here and see what questions have come in at this point. Here's one that says, I think it goes back to the example problem that we showed for the strap across with the nailed connection. Says you divided by phi, but didn't you forget to multiply by phi? I hope not. The dirty little secret about LRFD in this particular version of the NDS, and I think we talked about this earlier, is that the phis actually cancel out in the design process. So I'm hoping the phi canceled out in that example problem. I'll go back and look at that and make sure. But that's the intent. That is being fixed also in the 2011 version of the NDS, which is coming out fourth quarter of 2011. And so, and again, there is an FAQ on our website that talks about that, the reason for that. But again, that'll be clarified in the next version. Okay, the next question that's come in. Maximum outer row spacing of 5 inches apply to all members regardless of width. Yes. You do want to maintain that 5-inch spacing. So what you do not want to do is put take a 2-foot deep glulam member and put a 20-inch wide steel plate on it. You're looking for trouble there with splitting of the wood member. So you're going to want to divide your rows of fasteners up so that they're on separate steel plates along the depth of that member. Next question, does C sub M have to do with cross-grain tension more than the hole size changing when the moisture content under fabrication is greater than in service? Cross-grain tension more than hole size changing is greater than in service. And it's probably a combination of both there. For the moisture adjustment C sub M factor, it is going to deal with cross-grain tension. It is going to deal with hole sizes changing in service versus as fabricated. Are reduced body fasteners the same as upset bolts? I'm not familiar with that term, upset bolt. So I have to plead ignorance on that one. But I'll now that you've stumped the presenter, I'll have to look that one up and see what that is. So, is there a way to account for the kink in the strap? Oh, very good question. If you have changes in moisture content across 2 floors in the going from first to second floor, the way to account for that is to make sure you're using dry lumber that's close to equilibrium moisture content at that rim board. So an engineered rim board is going to come in at close to 10% moisture content. So that's probably going to be close to equilibrium moisture content. And so the only other way to account for that, if you can't if you don't have a piece of lumber that's dry, is to use some sort of slotted fastener that would allow for vertical movement. But I don't think that'll work then, because then you don't have you won't be able to get your capacity. So the only other way to do that would be to go to a different type of threaded rod through the members and not use a strap across there. Well, the questions are flowing in, so I'm starting to lose track. Go back to split ring connectors and talk about how they work. I am sorry, we won't be able to take the time to talk about how split ring fasteners work in this session. We just don't have time. If you contact me privately, either by email or phone, I can talk to you about those offline. Does the 5-inch dowel spacing limit apply to manufactured lumber products like PSL, LVL, or glulam? Good question. I don't know specifically. I would suggest you take a look at the manufacturer's literature to make sure. My guess is that it does, just because you still have to deal with the potential for even those products getting wet before they get installed. But the manufacturer's literature is what prevails there. So check their literature and see if they allow those spacing larger than 5 inches. what are the benefits for using split rings, shear plates, and timber rivets? Those really get you up to higher capacities. If you look at the capacities in those fasteners, as you know, we limit fastener diameter to 1 inch for bolts and lag screws in the NDS. And so once you exceed those fastener diameters and you need higher capacities, you're going to have to look to a split ring or shear plate and the timber rivets as well, which give you a higher capacity. The split rings and shear plates do that by giving a larger bearing area of the fastener distributed in the wood member. The split rings or the timber rivets do that by just creating a whole bunch of very stiff fasteners in the wood member that don't have as much ductility as a traditional nail might have. Okay, clarification on upset bolts was upset threads, and that even that doesn't help me because I've not heard of the term upset threads. So you stumped the presenter twice. Sorry. Okay. Previous slide shows what appears to be a glue lam gusset plate with dowel spacing greater than 5 inches. At least that's what it looks like. I hope not. A lot of these drawings are not to scale. So go by what the dimensions say rather than what the picture shows. That 5-inch limit is as you know shown in the NDS text. So okay, does an exterior application like a trellis get considered as wet, wet-dry, or dry design condition? If it's an exterior application, and when you say trellis, I'm assuming that the connections are, or the wood members that the connections are in are directly exposed to moisture, then those would be considered wet in-service applications. Maybe I'm not understanding the term trellis, but it sounds, I mean, when I hear the term trellis, I've seen timber bridges with a trellis along the edge of the timber bridge. Those, in my opinion, would be external or wet service applications. What is the difference between a wood screw and a lag screw? Head shape, diameter, thread type. The difference primarily is the ASTM standard under which they are manufactured. The AS, or maybe it's, no, not ASTM, I'm sorry, ASME. For lag screw, the ASME standard for a lag screw is B18.2.1, and I think those dimensions are shown in Appendix L. And then for the wood screw, it's ANSI ASME B18.6.1. And so the manufacturing tolerances are all spelled out in those ASME standards. And again, are shown, so you don't have to go out and buy an ASME standard. The tolerances and dimensions are shown, or not the tolerances, but the dimensions are shown in Appendix L of the NDS. So I don't see any other questions here. Ivana, did you have any questions come in to you that I may have missed?
I've got one more here that just came in. Eli is wondering if isn't the wet condition synonymous to being submerged in water?
Okay, no. The wet service condition is anytime the wood member exceeds 19% moisture content. And so that can occur even with rain or high humidity environments. if they are sustained for any period of time. And we're getting deluged here on the East Coast the last couple of days with about 2 to 5 inches of rain. So any type of wood member or connection that's exposed to rain on a continual basis would be considered a wet service application. The question that we'll often get that maybe will clarify it a little bit is, what about the type of structure like in a park where you've got a pavilion? And the pavilion has a roof, but the sides are open. So the wood members, the trusses, if you will, up underneath the roof are exposed to the environment. They're exposed to the air and relative humidity, but they're not directly exposed to moisture. And in that particular case, we would consider that a dry application if the wood members are not directly exposed to rain or direct moisture. The relative humidity question, really, you have to be in the 90% relative humidity range for a pretty extended period of time to get the moisture content of your wood up above 19%. And so only in very high humidity areas, South Florida maybe, the Caribbean, I think you would see cases where you'd have moisture content above 19% due to relative humidity.
Thank you, Buddy. It doesn't look like we have any more questions. If you guys come up with anything or it strikes you later on in the day, you've got Buddy's information here. You can call him or find him at info@awc.org. Also, you can always get in touch with us here at Woodworks at info@woodworks.org. For those of you who may have missed the beginning of the presentation, it should be on our website at woodworks.org by the end of the week. And if you'd like to print a copy of today's presentation, I'm going to post the link to download the presentation again in the chat box one last time here before we go. So thanks again, everybody, for joining us, and we'll see you again the next time we have a webinar.